Hey guys, welcome back. To wrap up this semester, I'm going to start transitioning into more high school type material. And so today I'm going to do a brief history of computers and introduce you to a little bit of how they work. So for the longest time, people have been trying to simplify the process of calculation. And whether that was using your fingers or eventually using brass and water and things like that, people have been coming up with ideas. And over the centuries, these ideas have been put together, and somebody developed maybe some logic, and then somebody developed like a mechanical machine or something like that, and they were to put these ideas together in order to finally arrive at where we're at. So let's start some of the beginning origins of computing. So this is one of the earliest that I know of mechanisms for calculating. It was found in a shipwreck over in the Mediterranean somewhere, I believe, and it dates to around about 100 BC, or so they say. And whether or not they're right, I don't know. I'm pretty sure that it is very old. And it's just kind of a blob of coral because the wood box had eroded away, and then fish and something had grown on top of the brass. So they took x-rays, and they realized, wow, this thing's actually used for calculating. And so what did they want to calculate back then? Well, they were very concerned with celestial movements, and they understood that there was very cyclical and predictable. And so they were able to boil it down, if you will, into a set of gears, very complicated set of gears that they could turn the dial, and it would tell them when the next lunar eclipse would be, or the summer, or any of the solstices. So very, very, very clever. If you ever doubted ancient man, well, this should clear up those doubts. They were very clever and very capable. I mean, let's just pause on that for a second. I mean, you think about the Antikythera mechanism. It was a very hard and complicated device. And they didn't necessarily have the tools to rapidly create this thing. They had by hand meticulously create these gears without flaw so that they wouldn't mess up the calculations. I mean, you got to give them a lot of credit for what they did there. Here's a fun little aside on the topic of geared calculators. This is probably it at its finest. Right above me here is a picture of a artillery calculator. It can calculate the pitch and the angle in order to hit a target at a distance, and they put these on destroyers so that they could, of course, hit other ships on sea. And very, very complicated machines, because not only were the ships shooting a target, they were having to factor in maybe the Coriolis effect and maybe the curvature of the Earth, because these things would shoot like 2 miles or 3 miles. So anyways, these were all gear-based calculators, and there's videos on YouTube of I guess the Navy training guides of how these things work and the basic breakdown of the gears and different gear combinations and which mathematical operation they equate to. And so it's very, very fascinating, the idea of calculating with gears. But it's also a very, very, I mean, at the end of the day, this thing was extremely heavy and extremely cumbersome. And I tell you what, that handheld calculator thing, it blew this out of the water eventually. So eventually, people began to move away from like geared. Well, I guess they didn't, because they were using them on ships for calculations. But there's another subsection of theory and logic and computing, and that is logic. And this was a group effort by many, many different people over the centuries. Like I said, somebody developing a certain mechanical mechanism and somebody developing a theory. And so most of what we have today is based off of logic theory that was then translated into a mechanism. And so if we were to like define logic, that is the reasoning conducted or assessed according to strict principles of validity, right? So you want your computer to be very, very strict with what how it's calculating, not loosey-goosey. It's got to be very, very strict. And logic is, you could think of this as being like the statement, if I am driving and I am and it is raining, then my windshield wipers are on. And so that's logic. That's an example of logic, if you will. So basically, if those two conditions are met, then my windshield wipers are on. If it's just one, driving and there's no rain, my windshield wipers are not on. Or I'm not driving and there is rain, my windshield wipers are not on. So that's an example of logic, and this can be broken down into the form of electrical signals. Before we do that, let me just show you some fun examples of water logic. So believe it or not, people have developed ways to calculate using the flow of water. And they took these ideas of logic, if this and this, or this or this, and different combinations of these sort of statements. They were able to replicate mathematical operations, or whatever it might have been. And you can do that with any media. This, for instance, is water, like I said. Very, very cumbersome, and obviously, you can't just go tipping it over. It's got to be upright. So, anyways, it's a fun example. And in college, I had a teacher one time tell me about the early computers he was working with in cars. When people decided to start integrating computers into cars, they had very, very limited technology at the time. And they started by using analog computers, which were either hydraulic based or air based, or something like that, and but very bulky and big. It's quite something. But so these are the early stages of computing. Now, electricity, of course, was well known, but there wasn't a easy way to control the flow. Eventually along came something called the vacuum tube, and what it allowed was a small signal to control a much larger signal, and so therefore kind of creating, and you could take these vacuum tubes and you could form different gates with them, and then from there you could control the flow of the electricity and compile them together in order to create something fairly complex. Of course, you've probably heard of these rooms that were the computers that were the size of a room, and that's partially because they had these vacuum tubes and they had some intrinsic problems. One of them was heat. They gave off tons of heat, and so the cooling, of course, you can't put them too close together, and you would have to cool everything off as well. So, but anyways, and then they're not exactly small either. They're probably about the size of I don't know what, like a little Red Bull bottle. If that's a good example, I don't know. But anyway, so they're not small. They gave off a lot of heat, took up a ton of room. But yeah, they got us through some of the early phases of controlling electrical flow, and in order to create machines that could calculate. And then came the transistor. It rocked the world. Transistor radios, all these various things came about. Various technology came about as a result of the transistor. And why did the transistor change anything? Well, it allowed us to control the flow of a substance, that being electricity, but with the advantage of it being very small. So we could stick things much smaller. We could create much more complex calculation devices on a smaller platform. And the reason being is because these are simply crystals that are stuck together and there's no moving parts. The other advantage can be at times that they don't give off nearly as much heat, because they're not the simple functionality, the operation of the device doesn't require heat generation. Now it does generate heat, and that's a problem with computers and things like that. It's one of the ceilings of computing right now is heat dissipation. You've got a problem there that they'll have to kind of work through. But anyway, so this is simply a gate, and you can turn it on and off. You can stick them together to create to control the flow of electricity. All right, so that is basically the fundamentals of computing. And now today, we have computers with these transistors that are microscopic and stuck on a silicone wafer and just jam-packed together, giving us very, very complicated abilities, very, very extensive abilities. Okay, so now let's talk about MindTest. Let's bring you over to MindTest. Well, one of the wonderful things about a mod called Mesicons, as you're probably all familiar with, is the logic gates. Now, these are those gates that I've been talking to you about. They're pre-configured to do the various operations that have been sought over the years. Hence the name logic gates. Each gate has a certain logical operation. And here you can see all of them right here. But there are generally just a couple that we are going to be concerned with. And I should have organized these better. But I'll just kind of go through them one at a time. And just 4 of the basic ones that you'd probably be interested to know about. Here we have the humble AND gate. It is probably the most friendly gate that there is. And in MindTest anyways, the gate accepts its inputs from the side. And so I have 2 switches here which represent signals coming in. And then of course out here we have the signal going out and then a light strapped onto it so that you can clearly see what it's doing. So if I start playing with these signals, you'll notice something about the functionality of the AND gate. So far we've turned on different signals. The 2 different signals, each on their own, and nothing has happened. But as you might expect with the AND gate, only if both are on, if the left and the right are on, then it will turn on the signal. So that is the AND gate. Here again is one of the very, very simple gates that we have, and this is called the OR gate. And so this will turn on the signal depending on the 2 inputs. So we have left input and right input. So if the left input is on or the right input is on, turn on the light. So that's what you would expect. So if we flip the left on, indeed it turns on. And then we turn that off, turn the right on, it does turn on. And then also, if you turn either on, it doesn't care. Which seems a little bit strange and might not be what you would expect. And so therefore, somebody has created, a long time ago, a gate to deal with that issue. And I'll show you that in just a second. So here is the XOR gate, and this deals with that very problem that I mentioned. It's XOR, and the X stands for exclusive OR. So if I flip on the left, it turns on. If I flip on the right, it turns on. But if I turn both of them on, it turns off. And you can tell that it is an OR gate because over here we have the traditional OR symbol. It looks like a D with the back kind of bent in. But then it has that extra little symbol line there. And I don't really know if there's any reason behind the selection of these symbols which would help you understand or memorize them better. I think you just have to memorize them, if you really have to. You don't really have to for this class. So last gate that I want to show you is the NOR gate, and this is simply the inverse of the OR gate, and it just flips the signal so that basically it is the inverse. So if you might remember, I don't know, but the OR gate, when both signals were off, the output was off, but in this case the output is on. Now for any other setup, the signal will be off. So it just helps you flip that signal. And by the same token, the AND gate has the same. It's the NAND gate, and it's just the inverse. Now, logic gates are very, very well documented. There's a ton of information about logic gates. This idea has been thought about for a long time, documented, right? And so people have put these different gates together for different purposes. and different functions. So what I thought would be fun is to don't try to reinvent the wheel. Go find a logic gate schematic. So that's what I typed in, logic gate schematic in Google. Find one that has a minimum of 5 gates. Combine them together as the schematic shows as best you can, and it might be difficult. You might need to do different layers, right? So you have, because you can see here we have different connections, and some of these wires are sticky, so they'll kind of connect to each other if you get them too close. So do your best. You might need to use some insulated wires and whatnot, but at any rate, I can answer that question later on in class. For now, let me explain. Just five different gates that are put together in a schematic. Put them on Mindtest and see what it does. These, of course, the ABC is the input, and then on the right we have the output. And so these are very fun to kind of mess around with just to see what people are doing. So that's your assignment. Make your own little computer using logic gates. Thanks for watching, guys. Talk to you next time.